Hello, class. So this is the first lecture. We're going to talk about some basics in epidemiology, measuring morbidity or mortality. And you should have had some background about this, but nevertheless, this is a very important topic, so we're going to go over it. And then in the class, we'll going to go over more examples. So don't worry if you don't get it all from the video, but I do want you to prepare for the discussion and the examples in class. So the learning objective is to be able to calculate incidence and prevalence of disease and differentiate between incidence and prevalence, as well as cumulative incidence and incidence rate, calculate mortality and the different aspects of mortality and morbidity. So the natural history of disease is what really kind of dictates how we identify the disease and the incidence and the prevalence. It's all related to this onset. So if we can look here, the onset of a disease starts right here. So let's say we're talking about the coronavirus. You know, somebody gets infected and they are at this stage. So that's where they start in the onset. And then there's a period before the symptoms appear. For example, fever, others. And so this is a period that they can still transmit the infection while there are no symptoms. But once the symptoms are there, it alerts us that, okay, this person is diseased, so then they have to seek care. And then based on that, they will be diagnosed. And then based on the diagnosis, they might need hospitalization and treatment. And then after the treatment, they either, you know, hopefully get cured, maybe become disabled, or if it's unfortunate, severe, they would die. So this is the stages of a disease, and therefore, when we have an outbreak, we would want to catch the disease and get the data. Now, we're talking about data collection as early as possible. Why? This is for incidence. For prevalence, it's not as critical. We can get it at time of diagnosis or at the treatment, because this is an ongoing, prevalence is ongoing, while in incidence, we wanted to know as early the new cases. So you can see why the data collection and the purpose of the data collection will vary according to when we get the data. So, so this is why it's important for morbidity to know the natural history of disease. Otherwise, we cannot differentiate or we are not able to collect that data. So, so this is, you know, as I mentioned today in the kind of outbreak of corona, what they do is they see the temperature of a person to check if they have fever, but that would be at the symptom stage, and they might have already had the disease beforehand, and there is lack of awareness, and they still are able to transmit the disease. We can talk about this, but in terms of incidence, of course, you could imagine if we miss those cases who are before the symptoms, we are missing the incidence. So when we say we have, you know, several thousand cases of corona or COVID-19, what is called, there's actually an underestimate, because the incidence is higher because there are people who have the onset but don't have the symptoms. They might be carriers, they didn't develop the symptoms. That is the incidence, that's the true incidence. In terms of the data on the prevalence, we can get it from any stage at hospitalization, either from the patients themselves. They say, we ask them, were you hospitalized? Or we get it from the physician, or we get it from the hospital records, or from national registries like the cancer registry. These are the most common ways to get the data on prevalence. Now, it affects the prevalence accuracy, because if the data is not complete, then we are missing a lot of prevalent cases. And these prevalent cases are out there in the community, but they didn't get recorded by the registry, or they didn't get hospitalized, and so on and so forth. So that's also one of the problems we face with data collection on morbidity. So in this case, in rheumatoid arthritis or dementia, the classification, and this is described in the book, can vary. So in terms of rheumatoid arthritis, there are many ways of classifying or diagnosing or documenting rheumatoid arthritis with different criteria. So if you're using one criteria, you're going to get a different number of cases. You use another one, you get a different number. So that's one of the examples that are in the book. And in terms of dementia, the same thing. We have, how are we going to calculate data or get data on dementia when we don't have an exact criteria of identifying that? The other aspect is women with hysterectomy and uterine cancer. So if we are trying to see uterine cancer in the population, we have the cases in the numerator and the people who are at risk in the denominator. What happens is, and of course they have to be women because it's uterine, so it's not men. So if the people who are in the denominator, the women, if they had hysterectomy, that is the removal of the uterus, then they are not at risk. So if they're still included in the denominator, what is this causing? What is this causing to the calculation of the prevalence? Think about it. If we have women who do not have a uterus, yet they are put as those who are at risk. So we can discuss this in the class as well. So the issue of morbidity measurements is that the quality of diagnosis, who has the disease, as we gave examples, the rheumatoid arthritis, dementia, they can undermine the quality of the data and therefore the accuracy of our measurements of prevalence and incidence. How we identify the cases will also have important implications, especially to incidence. So we have to, for example, conduct a research study, do an interview, get questionnaire data, or if we use existing data, we have medical records or surveillance data. All these will dictate how the quality of the data is, and therefore the quality of our measurements, and that can introduce error and bias, as we will discuss in later lectures in this course. The other issue is the denominator problems. As we described in the issue of hysterectomy, let's say we put the woman in the denominator because we're assuming all the women will be at risk of uterine cancer because all of them have a uterus, but that doesn't take in consideration the women who have their uterus removed for one reason or the other. They're no longer at risk, and yet they are included. The same thing for ethnic groups, how we classify ethnic groups and put them, we want the risk in among African Americans. So all those who are at risk are in the denominator. But then do we really identify African Americans? All of them? Do we know the numbers accurately so we can put them? And all this dictates the problems of denominator. So why do we go into this effort? What is the application? We know now what is incidence and prevalence, but why? Then the main thing is that these measures will help us know how well is this population doing. These measures are very important in terms of planning, in terms of health services, in terms of budgets, in terms of risks. Like the very good example, now we're looking at coronavirus or the COVID-19. Without this data, we have no clue. If we have good data, then we know, okay, this country now is at high risk, or this county, or this city, or whatever that is. this is the data that then we plan accordingly. And you can see there are so much implications to this decision, financial, economic, social. A lot of things will be dictated by how accurate it is. One of the things that came across is one of the countries, Iran, is the second largest outbreak of the COVID-19. However, their data is totally off. Either intentionally or unintentionally, they did not have good estimates, and their data doesn't match up. There are more deaths than we predict based on the incidence from other countries. For example, the incidence is 2% of death in China or most cases, while based on the data we're getting from Iran, it's much higher. So that means the actual people who are infected are higher, and some of them are dying. That's kind of some of the importance of it. So we describe the disease, disability, behavior, compare such information and trends and risks. These are very obvious, important aspects and applications of the of getting the prevalence and incidence. And the other thing is we predict the probability. If it's going on a trend, then we know in 2 months, in 1 year, where is that trend going? And therefore, we can also plan this studies to determine the risk and potential interventions. Okay, so I'm going to kind of go into some of the definitions. You should already know about it, but I'm going to just go over it. That a ratio is a fraction. That means the denominator is a count of anything, and the denominator is a count of anything, and that's a ratio. It's different from a rate, which we're going to describe. So in this example, if we look at here, there are 3 diabetic men and 4 diabetic females. So how do we describe the ratio for this? In terms of diabetic men to diabetic women. And the ratio is important for us to calculate the relative risk and the odds ratio. So the ratio, as you can predict, is 3/4, or it's sometimes written like this, 3:4 ratio. But it's usually when we use it, it's 3:4. So that relative risk and odds ratio is a numerator over a denominator of some group according to the other group. So keep that thought in mind. What is a ratio? And you have the 3 men and the 4 women. So we don't add up. We don't say 3/7 by adding 3 to 4. No, it's 3/4. It's a ratio. Now, if we look at proportion, are a type of ratio, but the numerator is contained in the denominator. So we have the same cases, 3 men and 4 women, right? And so the proportion of all diabetic men is 3/7. So that's different from a ratio. You can see here that the 7 includes everyone. And what about the rate? The rate is a proportion that has time into it. So it incorporates time. How fast is the disease occurring? So the rates are used for incidence. Once you have time, then it is incidence that is involved. Prevalence does not have a time. So it's similar to a proportion, while a ratio is different. So in this case, we have the 3 cases, right, of diabetes, and the people who are at risk are 700 people. So they are in the denominator over a period of 1 year, or it could be over a period of 2 years. So then you just multiply this by 2 or by 3, or it could be not a year, it could be a month, right? So then it says per person per month. or per person per year, depending on what's the unit, then that is going to give us the rate. Remember this is going to be used a lot in incidence. And so this other step here is also important to know. We just multiply by a number to get this number to make, more sense, rather than 0.0043. It is 430 per 100,000. So this is just a math issue where we just multiply by a number to get this number be easily more identified, rather than a 0.0043. We say 430 cases per 100,000 of the populations per year. It just makes sense more, instead of a fraction of a person or a case. So remember this, because we're going to use it a lot in all over the course in terms of incidence. Okay. So the rate tells us how fast the disease is occurring, and the proportion tells us the fraction of the population that is affected. So the rates tell us how fast a disease is occurring, while the proportion tell us the fraction of the population that is affected. Okay, these are the two aspects that beware that multiple choice questions might come where they include time, or how fast, or how risky it is. Then you think this is a rate. If it's what is the prevalence, what is the fraction of the people who are affected without an issue of time, then this is a prevalence. So this is a definition of incidence. You should know it from previous class. Number of new cases of a disease that occur during a specified period of time in a population at risk. So we have three terms. New, right? They're not old or existing. They're new cases during a specified period, and in a population at risk. This is the incidence. The cumulative incidence, and a lot of people or students from previous classes get a little bit confused about the cumulative incidence. So please pay attention, and I'm going to try and describe this. Cumulative incidence is calculated using a period of time during which all of the individuals in the population are at risk, and time is not a unit. So even though it is incidence, it is a specific or special type of incidence where the time is not there. There's no person years. So if the individuals in the denominator were followed up for a defined period of time, then they are all followed up for the exact same period. We don't have people who are gonna be there sometime or not. And if I want to describe this to you here, so we have, let's kind of go back actually to the to this example. So we have two cases. The picture with a little boy, that is from the Ebola outbreak in Africa, and you can see the map below it that we have. This is where the incidence of cases of Ebola happened. All this area here, it was a deadly outbreak a few years ago, and now we have the COVID-19 or the corona, and this is at the time of recording. These are the countries here that have identified the corona, so it's spread and it's spreading. So if we wanted to calculate cumulative incidence, right? So the 5 cases out of 200 passengers were followed up, and they then we wanted to see that what is the cumulative incidence. So if I want to go back and describe this to you as a case, we can give the example of a airplane that has people who were all at risk, and then how many of those got the disease. So we didn't lose anybody. They were all they were all followed up for the full time. So in this case, the cumulative incidence is different from the incidence rate. So let me demonstrate this in a drawing. Maybe that'll also help you better visualize what cumulative incidence is. Okay, so I'm going to describe to you the cumulative incidence in a difference between cumulative incidence and incidence rate. When we say incidence, it's usually referring to incidence rate, but to identify cumulative incidence, we have to say cumulative incidence. So let's say a plane with 200 people took off from a city with a COVID-19 outbreak. So all of those 200 people are at risk. We don't know how many of them got the disease or not, but they're all at risk, right? So no one dropped from the plane. They're all there, so they're captured. They go land in the airport, and then immediately they're going into quarantine. So they're put in a building, right? And they're staying there for a week. And then after a week, 5 of them actually developed the disease. So they went into the hospital. So as such, when they went to the hospital, those are the cases, and those are the people, the 200 were at risk. With cumulative incidence, the main issue is we're not interested now in time, because everybody was followed for the same period. They were all there for 1 week. So we just ignore this, and then we just say 5 over 200. Everyone at risk. And the 5 is the cases, and that's the cumulative incidence you can see here. Again, to make it easier, we just multiply by 10,000, so we get 250 per 10,000, the cumulative incidence. If we wanted to convert this or calculate the incidence rate, you see the difference is we have per week. So we have here 1 week as the time, and we calculate it. Now, if it was 2 weeks, 3 weeks, 4 weeks, then it's 1, 2, 3. So the number is different. But here, just for sake of comparison, let's use the same thing, that they were only followed for 1 week. And then you can see the difference here is the cases are no longer here. They're not in the denominator anymore. That's the difference. And then we do the calculation. It's slightly different. Of course, if we follow them for a longer period, it's going to be even more different. And again, times 10,000, but also times 1 week. So the calculation is 256 per 10,000 per week. So once you have the time, then you know that this is incidence rate rather than cumulative incidence. So now I think it becomes much easier for you to understand when we have these graphs what it means to have cumulative incidence or incidence rate. So here we have these 200 people right here, right? And in the plane we just described, and we have 5 new cases that were developed, and during a period that we followed over whatever this period. This could be 5 days, 5 months, 5 years, whatever it is. But all of those people were followed up, and for the same period, and they got new cases, and the total people who were at risk was 200. So that's cumulative incidence. Now, incidence rate is the denominator consists of the sum of the different times that each individual was at risk. So if the individuals in the denominator were followed up for varying periods of time, that's usually when we use the incidence rate, rather than when everyone was followed at the same period, then we use usually the cumulative incidence. So this is another example here. we have the total people were the total people, number of people were followed up in this figure. You can see for 5 years. So what do we calculate? 5 times 5 people, each contributing 5 years of follow-up, then we have 25 person years, right? And the 25 person years is when everyone did not have the disease, let's say, or they were followed for the same period. But in the real time, in the real case, is that not everyone is going to be followed up for the full period. So if some people will die at year 1 or develop the disease or earlier on, so they're not contributing the same amount of person year, it becomes less. Again, I want you to think about this in terms of person year, and we're talking here about incidence rate. Forget now the cumulative incidence. We're just calculating person years, what it means person years. And that is the number of years where somebody was at risk. And now these 5 cases are not the cases with the disease. These are cases that started, forget about the 200, forget about the cumulative incidence. We're just talking about 5 people who initially did not have the disease, or we're not knowing if they have the disease. We follow them up, and they contributed 25 person years. They contributed to the person years. But in this case here, they didn't all continue to 5 years. Some of them dropped, some of them died, some of them got disease. So then each one we calculate for them a different time period. So for year 1, how many people were there? 1, 2, 3, 4, 5. So there were 5 person years contributing. In year 2, how many were there? This person stopped. They're no longer here, so they did not contribute. So if you calculate this way, you have 1, 2, 3, 4 person years. So see, 4 person years in year 2. Year 3, we have 1, 2, 3, because this person no longer contributed. So year 3, there are 3 person years contribution. And year 4, they have also 3. And then year 5, there's another one who dropped, so we have only 2 person years. So we add these up and then become 17 person years. That's why incidence rate is important, because then we can try and compare the risk when not everyone is contributing and the numbers are different. Think about this and the examples we talked about and why time is important for incidence rate, and we can go over some more examples in the class. So it's a measure of risk, that is the incidence rate. And there's people who are going to move from the disease to the non-diseased status. So like we saw in the airplane, when the 5 cases happened, they became in the numerator, and the denominator was subtracted by 5. So it becomes 195. So they no longer are in the denominator. And it's described as rate per so-and-so population. 10,000, 1,000, whatever the population number we used. And there's a follow-up of people in the denominator for different periods. In a period that could be month or years, it says person month, person year. In the example in the airplane, it was person week. And the numerator only refers to new cases during follow-up and not existing cases. In prevalence, we can use existing cases. The denominator can be a combination of different follow-up periods for different individuals and includes a time component or followed up for an entire specific period. So the cumulative incidence does not have time. So remember this. And the individuals in the denominator must be at risk of the disease. That's obvious. And as we said, if somebody develops the disease, like the 5 people, they no longer are in the denominator and they become in the numerator. Again, we do screening to always find the new cases. A specific population or a subsample is followed, and there should be no numerator cases among the denominator population at the baseline. So when we start, We cannot put people who are already diseased and follow them up. That messes up the incidence. We have to begin with people we don't know who are the diseased and see what's the risk among them. If they already have the disease, it's no longer incidence, it becomes prevalence. So we are looking for new cases in those otherwise healthy population. Better measure of disease etiology than prevalence. These are some of the causes where people do not complete follow-up. There is no more follow-up, like they die or they are no longer in contact. Let's say we have a cohort of 1,000 people. After 1 year, we contact them again. We're not going to find the 1,000. Some of them died. Some of them, we lost their contact. Some of them have the diagnosis. Therefore, we are no longer going to count them as being part of the follow-up. They are cases, so they move into the numerator. If they, in some cases, we're following myocardial infarction. If somebody developed angina, then they are what's called an intermediate disease, because angina and myocardial infarction are related. So we no longer can include them, continue to include them in the follow-up. They have to be excluded. So let's kind of talk a little bit about prevalence, because the prevalence is the most important thing after incidence to know in measures of morbidity and mortality. Prevalence is the number of affected persons present in the population at a specific time divided by the number of persons in the population at that time. So we're not subtracting, we're not following up, it's just at a certain time. The numerator does not include new cases only. It includes old and new cases. There's what's called point prevalence and period prevalence. We're not going to use a lot of these differentiation during the course. When we say prevalence, it's usually period prevalence. During a certain period, what is the prevalence during a year or a month? And the main difference within this incidence is, I'll leave it to think about you. What is the difference between prevalence and incidence? We already talked about that. So it's not a measure of risk, it's a proportion. There's no follow-up. Includes old and new cases of the disease. The duration of the disease or when the disease occurred becomes irrelevant, because some person might have the disease years ago. And somebody just got it last night, or it doesn't matter. When we come today and we're calculating what is the prevalence of diabetes, some people have had it for a long time, some people just had recently. It doesn't differentiate, unlike the incidence where we're only looking at new cases. It's usually not practical to screen people during a point of time, and therefore time is not taken into consideration to differentiate point and period prevalence. And again, the prevalence can vary over time. Prevalence of flu in certain season, or asthma in a certain season, will be different from a prevalence in another season. So it's kind of something that is a moving target. However, it's very useful, is telling us what is going on in the population in a certain period of time. So it's like the snapshot. This picture in a mall, or this is the actual, not the mall, this is the train station in London. And so there's a snapshot. Those are the people in this picture. This is what prevalence is. After 2 hours, you come, you have another snapshot. It's a different number of people and different. So that's kind of an idea of what a prevalence is. Now, we can go over this as well in terms of what is the prevalence of a disease in a certain period of time. So in this case, in a population of 1,000 people, right? 1,000 people. What are those people who are in these lines? Those are people who developed the disease. Okay, so some of them, like those people here. So what is the prevalence of disease in 2014? So prevalence of disease in 2014 means that this period here. Forget about this and forget about this. How many people have the disease during this year? So that's one person. That's 2. That person, although they develop disease here, there's still disease here, so that's 3. And then that's 4. So we have, oh, and this one. We almost forgot that one. So that's 5. So 1, 2, 3, 4, 5 people, right? 2014. So you divide 5 by 1,000, and you get the prevalence. If we go, what is the prevalence in 2015? It's a totally different number. If you go to 2013, what is it? It's also a different number. So that gives you an idea of, here you can see the prevalence. Again, we can multiply by 1,000 and we say 5 per 1,000 just to make it easier. It does help us in trends. So this is a case of trends of cancer in Jordan. And you can see immediately, like this is a prevalence of all cancers. Immediately there's a hike here. And then the prevalence showed that there's a huge increase. I want you to think about it. Why did we have this hike in this period? Okay. So introducing new screening measures can produce inaccurate prevalence trend estimates. Cure or death can decrease overall prevalence. If we have a lot of a new treatment, then suddenly we have less cases, so the prevalence changes. Or if a lot of people are dying, then we are having lower prevalence because they're no longer there, they're dead. If we're looking at a disease prevalence. Prevalence is useful for health planning. It assesses the burden of the disease. It gives us, an idea of the access to health, because if we have better access, then we will think, oh, there are less diseases, but actually it's just because we have better healthcare in this city compared to the another city. So more patients will not die, and therefore the prevalence is increased. Like when insulin was introduced, suddenly we no longer have deaths from diabetes. So the prevalence increased. We have better treatment and better survival, but the prevalence is showing higher numbers, so because of the insulin. Prevalence can also be used for behaviors and not just morbidity. So think about physical activity, prevalence of physical activity, or prevalence of smoking. It's not just disease. It's not good for etiology, for causes, but it has a role in knowing, what's going on in terms of chronic diseases in the population. So I want to compare now the incidence versus prevalence. We can actually have this to help us know or learn how prevalence is increasing or incidence is increasing by this formula. So prevalence equals the incidence times the duration of the disease. And this is making the assumption that the disease risk is not increasing, or there isn't an influx of new disease cases and so on. So in a steady state situation, prevalence increases if only incidence increase. So if you say, let's say this is 10. Oops. So let's say the prevalence is 10. So and the incidence is 5, and the duration of the disease is 2 years. So 2. So 5 times 2 is 10, right? So prevalence increase if the incidence increase and there's no change of duration. So this can increase and becomes higher if the incidence is also increasing and this one is not changing. Or if both incidence and duration or both increase, of course that will increase. Or if this one increase but this one is not changing. So if either one of these increase or both of them increase, of course the prevalence is going to decrease. Prevalence will decrease if either of them decrease or both of them decrease. It's obvious, this is math. So think about it, and these numbers, and you can solve several of the examples we will have during class. Want you to look at the example in the book about high town and low town, how positive x-rays showed that those who are in the high town have higher cases of TB, but because the high towns survive longer, they have higher prevalence. So it shows that they are, there's more risk, or there are more diseases in the high town, when actually the people in low town are dying. And therefore, that is the reason that it is lower in prevalence. We can talk about prevalence at birth for malformation better than incidence. That's something that it avoids those who are aborted and focus on at birth. Again, this is described in the book. I'd like you to look at the book, and these examples are very nicely explained. Again, the example of New Zealand increase in extramarital births. That is actually a decline in marital birth while steady extramarital birth. It's not because there is increase in extramarital birth. These are all these shifting that can give us misinformation if we rely on prevalence. So that's why rates are more informative. They avoid these problems if we look at rates and incidence. This is how the prevalent cases are different from the incidence. So you can see here, we identify initially a population, determine who has the disease and who doesn't have it. So those who have disease, the prevalent cases, we don't follow them up. We go and follow those who did not have the disease. And then we see at the end, after 1 year, who developed the disease. These are new incident cases and who did not. And therefore, we can calculate the incidence rate. This is another example. This is, again, from your book, and how the baseline prevalence can change based on if we have new cases of incidence, then the prevalence is going to increase, right? Or if the deaths or cures are more, then the prevalence is going to decrease. Or if there's a steady state where the incidence is coming at the same rate as the deaths and cures are here, so then the prevalence is not going to change. These are the relations to the equation we just described. Okay, I'm going to give you this example, and I want you to come and prepare and explain that in the class. For lung cancer, what is happening here? This is male rate, and then female rate, the red, and this is the age. And you can see here that this is the rate per thousand, and then why are these numbers different? Let's come and prepare and discuss it in the class.